Okay, so welcome you all. I'm really glad to introduce the speaker of today, Barbara Mazzolai. I'm grateful that she accepted our invitation. Let me just say a few words of presentation of the speaker. So Barbara received her master in biology at the University of Pisa in 1985, and after that a PhD in microsystem engineering at the University of Roma. And after that, she held a position at the Scuola Superiore Sant'Anna in Pisa as a researcher and then as a professor. And from November 2009, she was instead she moved to IT in Genova, and she was a team leader of the Center for Micro Robotics in the IT Institute of Genova. And from 2011, she is the coordinator of the center itself. Let me just tell you that Barbara was a recipient of the Marisa Belisari Award for scientific and management activities in the EU Dustbot project. And she also received in 2012 a medal of the Senate of the Italian Republic for scientific activities in biomimetics and biorobotics. She was also listed among the 25 women in robotics you needed to know about in 2015 by the RoboHub, which is a leading international community in robotics. The interest of the research activity of Barbara concern mainly, among all the others, the Bioinspired soft robotics, which she's going to speak today, design and development of new Bioinspired technologies. She's the coordinator of various projects, among which I just mentioned the Plantoid Open European project. She's associated of various German biorobotics in soft robotics, and she's a member of the IEEE and Robotics and Automotive Society. I'm really glad that she's here to speak today. Please.
Thank you, Fabio, for the kind introduction. And, good afternoon to everybody. It's a great pleasure for me to be here, invited by the colleagues, and it's also hopefully a great opportunity to share my activities and try to establish some collaboration in the future. So mindfulness robotics is something that we need, in fact. And my area, as Fabio said, is Bioinspired soft robotics. And I would like to start from our method and methodology. So that is, in fact, deeply funded and based on biology. So our approach is first try to identify the biological system that we want to imitate for making, of course, innovation in robotics and engineering, and imitating some specific function of the biological system, like locomotion, materials, components, and so on, for some specific application, and then I will show you some idea that we have in mind. But at the same time, our approach is try to use this robotic platform to better understand the biological systems that we take as a model. So our goal is doing science and engineering at the same time. And so I will try to explain more in detail what are our approach during the presentation. So, but first of all, why bioinspiration is so relevant in robotics? If we consider traditional robotics, industrial robotics that all of us know very well, usually in this case robots move in what is called a structured environment. So the robots are pre-programmed and they can perform predefined tasks and activities, and the interaction with the human operators is limited for safety reasons. But if we try to imagine to move robots in our environment, real environments, at that point robots have to face with a changing condition, uncertain situation, and what is called unstructured environments. So at that point, take inspiration by biological system can really help in design these new robots. And very important is also the interaction of this robot with the human operators and other living organisms. So, I mean, inspiration can really help in technology. There are a great example of robotics that come from nature in many different areas. So just to mention some of them, in coordination, so there are several studies about the swarm intelligence in ants, in fish, or in birds, and then translating robotics application or in artificial intelligence. Learning, of course, is very important in robotics, and the goal is study how humans learn. And this is the iCub robot that is made by my colleagues in Geneva. And this is actually a robotic platform for neuroscience. So neuroscientists use these robots to validate some models on learning in humans, in fact. Adhesion is also very important. This is the robot developed by Mark Budkowski in Stanford University, and in which they try to imitate the climbing properties of gecko. So they are able to climb in vertical condition thanks to the hierarchical organization of the hairs in the foot, and also the control given by the position of the legs and the tail. And then manipulation, and in particular I also mentioned the activity that we have performed in Scuola Sant'Anna about the inspiration by octopus to develop a softer robots, in particular for manipulation tasks. So Bioinspired is, I mean, there are many examples in robotics at different scales, at different level of complexity. But of course, if we consider biomimetics or the Bioinspired approach, this is not new at all. If you consider that Leonardo da Vinci studied living organisms to do innovation in many different fields, including engineering. So he studied, in fact, the bird flight or designing flying machines, or also the human anatomy, because it seems that he designed the first humanoid, the mechanical knife. But what is also evident is that most of these machines were never fabricated by Leonardo, because probably there was a sort of technological gap. So Leonardo didn't have the right technology, where the right technology is the fabrication technology, I mean the materials, the energy forms, the actuation. And in fact, quite recently, a group of students in the University of Toronto in Canada developed an ornithopter, so an aircraft, starting from the original design of Leonardo da Vinci. So demonstrated that, in fact, I mean, this is a problem that we have to face every day to transform, I mean, living organism principle in technology. So we need new rules in all the fields. And in fact, we needed to change completely the approach in robotics. So rethinking robotics, take inspiration by nature. So we need a simplification mechanism, new materials, fabrication technologies, control, I mean, control rules, energy forms. So the idea, as I said, is look into nature to transform, of course, by simplifying this principle in technology. And we need also new approach from a technological point of view. So soft robotics is in fact a new way to develop new materials, new bodies that are more compliant with the environment. So soft, in fact, means soft to touch. Touch is fundamental in living organisms, but it is also fundamental in our robot. They have to explore the environment, they have to interact with the environment, with the other organisms, with the humans in a safety way. And also emotion is very important, because this is especially fundamental in human-robot interaction. So with a softness we can express, I mean, the feeling, and this is very important in robotics as well. So there is also another principle that is coming in robotics, not only materials, that is fundamental, so rethinking our robots also in terms of control. And there is this new paradigm in robotics that is called embodied intelligence. So in the classical approach, the focus is in fact on the brain and the central processing. But now what we try to do, especially take inspiration by nature, is giving importance not only to the brain, but also to the body, to the capability to interact with the environment. So, and in the example of the robots that I will show later on, we try to implement, in fact, the embodied intelligent concept, especially taking inspiration by this kind of animal, the octopus animal, that we used in 2009, Scuola Superiore Sant'Anna, as a paradigm to demonstrate the importance of the body, the importance of the morphology, the interaction with the environment. So we proposed this fat proactive European project named Octopus. And we proposed Octopus, as I said, as a model. So this was the first soft robot inspired by this animal. But why Octopus is so important in soft robotics? First of all, this animal doesn't have any rigid skeleton, rigid structure, so it can move in any direction. So in principle, it can have an infinite degree of freedom, can bend in any direction. But also, at the same time, because there are no skeleton, it can squeeze and move in any environment, very narrow spaces. But at the same time, it's not just soft. They can contract the muscle and apply strong force to the environment. And this is very important in robotics as well. So they are able to control the stiffness, that is an open issue in soft robotics. They can manipulate, express a different kind of locomotion capability. But very important, this is a very smart strategy. Most of the neurons are in the arms, not in the brain. And so if you look to the organization of the nervous system, there is a central system with about 50 million neurons, then an optical lobe system that are very sophisticated in octopus, because the eyes of octopus are very similar to our eyes. And there are about 60 million of each lobe, but then 40 million neurons for each arm. So most of the neurons are in the peripheral nervous system. And this is the secret to control many degrees of freedom. And then, of course, the interaction with the environment is fundamental for the octopus. The other secret is in the arrangement of the muscle inside the arm. So there are different kinds of muscle, longitudinal, transversal, oblique muscle, and they can contract this muscle in a selective way, and the volume remains constant during the contraction. This is another secret. So, what we can learn from octopus? First of all, that we don't need bones or rigid skeleton. This is true, in particular, in water, in fact. They can reach a very large dimension. It's less true in Earth, because usually, of course, there are very small animals completely soft on the land. But this is important, interaction with the environment. And we don't need much central processing for control. We can also distribute the control in the peripheral arms, depending by the morphology, of course, depending by the structure. So this was our approach, as I said. So first, try to extract some key principles from the animal. So we developed several setups in order to quantify some motion functionality in the octopus, in the animal. And so we developed this non-invasive setup to measure, for example, the elongation of the arm. This is very fascinating because the octopus can elongate the single arm more than 70% with respect to the rest position. And the secret is that they contract, in fact, the transverse muscle in order to elongate. So also from a robotic point of view, we develop the transverse muscle in order to elongate our robotic arm. So it's a sort of passive elongation. And then we measure the force. They can pull more than 40 newton with just one arm. And then other features like the arrangement of the muscle inside the arm, the nerve cord arrangement, and many other features. And we use all this quantitative data, this information, for define our specification for the design of the robotic arm. So we developed a different kind of setup and a mock-up, so in order to test some specific function. In this case, we tested the bending capability that is given by the longitudinal cable that starts from the base to the tip. So 4 cables, and then additional cables at different point of the arm in order to selectively contract the cable, the actuator, and so to change the stiffness. In order to elongate the octopus arm, we use these shape memory allow actuators, spring, that are very sophisticated because when a current is applied, they contract, and so we can imitate the contraction, the transversal muscle in the real octopus and having the passive elongation. So then we integrate all this function in the robotics soft arm, and so we have a cable for bending, as I said, in all the direction, and this is very important. The robot is in water, in marine water, because the density of the natural animals is very close to the density of the seawater. And this is also very useful because it helps the octopus, the real octopus, and the animal. So we use the same strategy in our robot. So then we have the bending. We have when all the cable and the actuator are contracted, the octopus arm becomes rigid. And then we can have the elongation by the contraction of all the SMA springs actuator. This is just a view of the SMA springs actuator in order to have the elongation. And then we have the full octopus robot with 8 arms that have a different function. So the frontal arms are used for grasping, and the rear arms are used for locomotion, like in the real octopus. So there is this crawling mechanism, the crawling locomotion that is very useful and common in the octopus animal. In terms of application, when we started the project, our basic idea was to use the octopus soft robot to move on the bottom without any damage for other living organism or to the bottom itself for archaeological rescue application. But then, this is very interesting for me because we had the idea together with the King's College London to use the capability of the octopus to change the stiffness, to create an endoscope, a manipulator for surgical operation. So in fact, the endoscope can be soft to move inside of the body, but also rigid when they have to operate and to perform a task inside the body. So this was one of the new application, also very far, if you want, from the original idea. And I think that this is the challenge of this activity, of this research. So in many cases, we don't know in which direction, what are the potential applications of our technology. So as an IIT, we are also studying the octopus suckers because they are really amazing, because most of the sensors are inside the suckers. The octopus uses the sucker as fingers, in fact, to manipulate the object. And also very interesting, from a robotics point of view, the suckers, the octopus can adhere to any surfaces, not only smooth, but very unstructured surface. So it's very nice because we can use it for industrial application, domestic application, for developing climbing robots as well. And the approach is the same. So we started from an analysis of the anatomy of the octopus sucker using different technology, MRI, ultrasound, in vivo, histology, and we discovered first some anatomical parts that were never described in literature, so this protuberance was never described, and also we discovered the presence of hierarchical hairs in this area. So it seems that these hairs are fundamental also in wet adhesion, not only in dry adhesion. And in fact, we also found the similar hairs also in a fish, a species of fish that have a ventral sac to adhere to rocks, and also some kind of mollusk. So it seems that this is also relevant in robotics in the future. And we discover the working principle of the sucker adhesion, and again we use all this information to have a reconstruction of the sucker. We use a CAD model to have a molding, to make a molding of the sucker with the same anatomy, with the same materials. We select artificial materials very close to the natural one in terms of mechanical properties and capability to adhere to any surface. And very interesting, also our suckers works very well in water. So again, environment is very important. So we needed to design our system, our robots, considering the environment in the design phase. And then, of course, we are moving on an active sucker, embedded soft actuator inside the artificial sucker. And this is also related to octopus. We try to imitate together with this group in USA, the Cornell University, led by Professor Robert Shepard. We developed this skin, artificial skin, that can stretch, sense pressure, emit light, try to imitate, this is the first tentative, to imitate the camouflage properties in octopus and cephalopods in general that are fascinating. In octopus, not only the animal is able to change the color immediately, as you know, but also the shape, the texture. So this is very interesting also for future application. And so this is a sort of capacitor made by soft materials, embedding copper manganese in order to provide the color when it's a stretcher and when an electrical field is applied. And so we can use in the future for many different applications, for making, for example, multi-pixel display that can change the color when it's pressed, or also having a crawling robot or a soft arm that changes the color when interact with the humans, for example. So this is related to animals. The activity, we are other activity related to the animal kingdom, but I would like to go a little bit more in detail about our recent activity on plants. So for the first time, we introduced plants as a model in robotics, and we propose, in fact, in particular, plant roots as a model to develop a robot that we call a plantoid, that is designed to move in soil for environmental application, soil exploration. But when I started in this research some years ago, the community was not so open, no? Because the common feeling towards plants is that they are quite passive organisms, not able to move, to interact with the environment, to communicate, to perceive. But in fact, this is quite incorrect. This is not true at all. They move in a different way. So the movements are not based on muscle, and they usually are not visible without an acceleration, even if there are also very fast movements, like in the carnivorous plant. This is the Dionea muscipula, the Venus flytrap, that close the leaves to eat animals in less than 1 second. These are very important movements. The tropism is the name. So they move growing, and this is very peculiar condition in plants. In order to move from one side to another, they have to grow. There is no alternative. And they grow following or escaping from environmental stimuli. This is very interesting. They communicate with plants, communicate with animals, with the bacteria, with the fungi. And they establish, so this is something that we are investigating in our group, they establish a network with other roots, and also together with the eye for fungi, they create what is called a wood wide web. So a network under soil that can be investigated to extract the algorithm, to control the robot, but also to be applied to many different fields. So all these activities are something that we are trying to transform in robotics solution. In particular, as I said, try to imitating growth in robots. If you consider growth in animals, most of the growing process happens before birth, and it's called determinate growth. So animals reach maturity and then stop to grow. In the case of plants, they continue for their entire life. So this is called indeterminate growth. And this is exactly the concept that we want to imitate in our robots. So movement without muscle. So we can generate a new plethora of actuator and strategies and control, take inspiration by this concept. So we study all these movement in plants. There are many. Some of them are passive, others are active, with or without metabolism, reversible. And we start, as I said, for study plant roots. So the secret of the plant roots is that they grow at the tip level. So they have the cell at the tip level, then elongates, taking water from the environment. And this is the secret, because in this way, the only part that is moving in the soil is the tip, to avoid the pressure and friction that are very high in soil, a few centimeters. And at the tip level, they have the sensor, so they perceive the environment, they touch, they perceive gravity, water, chemicals, dangerous parameters, so they avoid pollutants and so on. And of course, the behavior following the gravity is a sort of worm. The behavior is very similar to worm movement. And they created this network, and we want to understand if there is communication among the apexes in order again to extract the swarm intelligent roots, apply in this case to the roots, not to the animals, and then control our robot using this algorithm. So why again plants? When I start, the point was, but there is moles, there is earthworms that move in soil. Why you want to study plants? So the point is that they are very efficient, but if we consider invertebrates without legs, so they are able to generate a crack in the soil, to anchor, and to elongate. If you consider the earthworm that is very well studied in biology, they have a liquid inside. When they contract the transverse muscle, they elongate. When they contract the longitudinal muscle, they enlarge. They create in this way the crack. They anchor with the seten, with the hairs to the soil. And this is also true for Arenicola marina, that is another vertebrate, mollusk-like these that have this foot that elongate in the soil. But if we consider also a very simple plant, like rye, they have 1 million of apexes in the same root apparatus. Then they generate hairs in order to anchor to the soil, to be more efficient during the penetration. They can generate a crack in the soil, enlarging the diameter here. And so, in addition to that, they grow for the entire life. They create a permanent structure that is very useful in many applications. I will show you later on in which way, and they create a network. So they explore soil in a capillary way, so they are much more efficient and they have a much more sensor than the other animals that I mentioned before. So this is our model, and in particular, we want to study here the secret, the cell division and then the elongation. So how they can penetrate a very strong soil, because they can destroy everything. They can move in any way. So this is the secret. And this is what we have to imitate, growth. So for the first time in the world, we developed the first robot that is able to grow. And the secret is that here there is a motor that pulls a filament in a spool. Then I will show you the final picture. And the new filament is always in contact with the tip. So also in the robot, the only part that is moving is the tip. This part doesn't move with respect to the soil, so there is no friction. And in fact, this is the internal view. There is a motor, as I say, that pulls the filament. There is a sort of gears that allow the perfect deposition of the new filament in contact with the tip. And then
we try to compare the growing from the tip with a system with the same dimension that is pushed from the top, because in biology we know that they grow from the tip, but we don't know why. I mean, we never demonstrate why. So we use the system and we observe that the elongation from the tip is faster, 40%, and also is a way to reduce the energy consumption. So of course, even if the size, the geometry of the robot is very different from the natural system, in this way we validate the principle, actually. But it's not enough, because roots are able to grow, but also they are able to bend to avoid an obstacle, to following or escaping from environmental stimuli, as I say. So we need to implement this kind of behavior, this differential growing. In order to bend, they add more cell in one side with respect to the other one, and they bend. So we try in different ways. We implemented several technologies. Just to mention some of them, we use these electrological fluids that have a dielectric nanoparticle inside, and when an electrical field is applied, the viscosity changes, so they become rigid, so the fluid becomes quite rigid. So we can play with this fluid, and we create some valves that can be open and closed in order to activate 3 chambers in a selective way and to have the bending. So this is a very nice way, because we can reduce the complexity. We have just a pipe as actuator, but the problem is the high voltage required for this kind of actuator, and it's not easy to integrate with a growing system. So we try to simplify our idea. We propose some soft springs that can elongate selectively in order to have the bending in all the direction. And we use for many different applications this system. But in nature, if we come back to biology, these 2 functionalities that we separate are in fact integrated, so they can grow and bend at the same time. So after more than 1 year, we developed several prototypes, and we tried several ways to translate this growing bending functionality in a robot. And then the idea was to take inspiration by the 3D printer approach. Instead to use a normal filament, we use a thermoplastic material. So we change with an heater the viscosity of the material. And if the material is deposited in a uniform way, the robot can move in a vertical position. If we add more material in one side in respect to the other side, the robot can bend. And this is in fact the current version of the robot, in which there is a thermoresistor inside. So we use a PLA, that is a thermoplastic material used in 3D printer machines, and we reach for a few seconds 200 degrees. So the material becomes sticky for a while, and the new filament can adhere, can attach to the previous one. And so in this way we can create the structure, and the bending is given by differential deposition in this way. So we tested the robot in air, simulating the pressure generated by soil, so up to 6 kilo, and also in an artificial soil in order to test the features of the robot with the temperature and humidity that can be controlled in some way, because soil are completely different each other, so it's not easy to test the robot in natural soil. So this is the current version. These are the sensors that are integrated in the current version. So temperature, gravity are commercially available. Humidity, touch, and chemicals are purposely developed by my group, integrated in the robot, in the tip. And there is a tropism associated. So hydrotropism, gravitropism, sensor plus a behavior that is associated to the sensor. But we use our robot also to test and validate another important movement that is in plants that are called circumvention. So what we know is that the roots move, also making oscillatory movements, but we don't know why. So Charles Darwin studied in detail this kind of movement, and one of the hypotheses is that circumnutation can help the robot in movement, in penetration of the soil. So we use our system to validate this movement. We test in ZEA mice, we use these plants as a model, biological model. We perform several experiments. We observe that most of the circumnutation are made in 1 hour. So they took 1 hour for making circumnutation. We consider different, we develop an algorithm that considers different stimuli, like gravitropism, all the parameters related to the sensor, and circumnutation. And what we observe is that, first of all, we extract the parameter. So the period around 30 seconds is more efficient in terms of force with respect to the depth, fixing the velocity and the amplitude of the movement. Then we select the best amplitude, and then we compare the system with and without circumnutation, changing the velocity of the system. And what we observe is that the best performance is in fact with circumnutation. So we in some way validate again the principles of biology, and this is a movement that we can integrate in our robot in order to be more efficient in real soil, in real penetration. So what we observe is in fact that using circumnutation, the system uses less, 80% less vertical forces. So then we study other movements. Some of them, as I said, is active. Some of them are based on osmosis. So this is very nice concept in plants, because in octopus we observe that the turgor, the stiffness, is changed by contracting the muscle. Here we don't have the muscle. So they generate rigid or soft material and behavior by means of water flow. So this is the secret in the plants. This is the mimosa pudica that close very fast the leaves when it's touched, and again is a loss of turgor at the base of the leaves. So we study this movement that is based on a flow of water from one side with the minor to one side with the major ionic concentration. This is the point. And by using a simple mathematical model, we extract the key parameter for the design of our actuator, in particular 1 minute time scale, because we are talking about forward osmosis, so the movement is completely passive. Then the length scale that is around 10 millimeter, so it's still big because the osmosis works very well at the micro scale, but this was the limit from a technological point of view. And then a maximum force around 20 newton. So we develop our system in which there are 2 chambers, one for the water, the other one for the osmolyte, that here is sodium chloride, an osmotic membrane, and a bulging membrane to show the movement. And this is very simple because we can just add water and the process starts. And the maximum actuation is in 1-2 minutes, so in the order of the natural system. And we really reach 20 newton as a maximum forces. So what we can do, again, we just develop some demonstrator to test the performance of our system. So we can also raise a 2 kilogram beam with just the bulging membrane, so it's very effective. Or we can have a faster movement in a preloaded system. Like in nature, there are many movements like this. But now we are trying to use this osmotic principle, forward osmosis, for drug release. We have a contact with a company for a system for a passive drug release in skin. Then I would like to show this kind of movement because from my point of view they are very exciting. These are completely passive, so there are no metabolism inside. These are dead organs, like a pine, but they continue to move thanks to the interaction with the environment. In particular, thanks to the arrangement of the material inside the cell wall. So there is a matrix that absorbs and dissolves water, and microfibers that, depending by the arrangement, give the movement. So they can drill inside the soil, they can bend, they can fly. And what is very relevant in robotics, that this is just the material that, because they are designed in a specific way, interacting with the environment, they can move without any metabolism, reducing the energy. So we developed a hydromorphic actuator that is based on a bilayer configuration. One layer, the P.PSX, that is a polymer, works like the active material. So the P. can absorb and dissolve water, and the PDMS works driving the movement because doesn't reply to the humidity. Because the P. is conducting material, we can also apply an electrical field, and there is, by Joule effect, water release and a bending. So again, we can have a different configuration. We can have a very small, soft hands for manipulation grasping. But what is very important for us is the message. We needed to design a different way our robot in which the materials have an important role because they can really interact with the environment, reducing the complexity of the control and also the use of energy. So this material can work as an actuator and sensor at the same time. To end this part, I would like to mention this work that was described by Charles Darwin and his son in The Power of Movements in Plants. They describe, in fact, the teeth of the root as a sort of brain of lower animals that are in the soil, perceive the environment, and take a decision. And starting from this idea, the question that we posed was why, in which way plants can manage all this information, all these parameters without a brain. So we started to think how to control our robot, take inspiration by this feature in plants. And we consider the priorities that plants give in order to move. So some priorities like following water, gravity, chemicals are given by the DNA. But then these priorities change dynamically thanks to the interaction with the environment and for the need of the plants. So water can be not a priority, it could be hydrogen or other kind of parameter. And the output of this algorithm is the growing rate to the robot for the deposition and the position angle for the direction of the growth. So we developed together with the FL a simulator in order to simulate the complexity of the soil, because in soil we have a lot of parameters, but it's very difficult to control from an experimental point of view. So we simulated different stimuli in the soil in this simulator, and then the output give the direction of the bending in the robot. This is just the starting point because we would like to move, in fact, in this direction, try to better understand the communication inside the root. As I said, this is a recent collaboration that we started with Professor Marcati at the University of L'Aquila, in which we want to really extract the roots from biology to develop a new algorithm, as I said, to control the robot, but also could be applied to many different fields to control the traffic, economics. Disposition of foods in the supermarket, like in the swarm intelligence that traditionally is inspired by animals. So this is the first tentative, but hopefully I will have other occasions with your groups to apply math to this kind of very complex problem. And this is the view, the full view of the robot, in which we have a trunk where is the electronics and the spool for the material that have been deposited in the roots, the branches with the material that I showed before that can reply to the humidity, and so works as a sensor and actuator at the same time. This is the secret. And then the sensor in the tip and the tropism associated. As I said, the behavior can be positive or negative. The root can bend, in this case, as negative, so the root tends to avoid high temperature obstacles, so they move far from an obstacle. And also hydrotropism, so this is positive, so they grow following water gradients or chemicals and so on. And then, of course, the root that is able to grow by a layer deposition, that is the the case. It's a sort of self-building, self-creating robot. So it's the robot itself that creates its body. So, application, I have a background in biophysics as well, so I developed a sensor and robots for monitoring pollutants in the environment. But soil is another story. It was in the beginning quite impossible to develop a robot able to move in the soil for the reason that I said before, pressure, friction very high. So only studying plants, in particular roots, we were able to develop this plantoid for soil exploration and in particular for environmental monitoring, because depending by the sensor that we integrate in the tip, we can follow water but also mercury or radon, so we can predict and monitor and give information to the human operators about the quality of the soil. But we also started with a space application. This was a very small project some years ago, funded by the European Space Agency, because of course the roots are important not only for exploration, but also for anchoring. So first of all, they had to anchor the structure and then the plant can grow. So we had this feasibility study dedicated to the plant roots. And for the future, this is a new line that we have recently launched in my group, my team. Take inspiration by this concept of growing. The idea is to develop a new endoscope that, because growth reduces the friction, the pressure, without damage for the external environment, and in this case the external environment is our body, our tissue. So again, the future could have this endoscope can be endowed with some sensor for detecting some specific target inside the body. So not only for screening, but also for drug delivery in a specific location of our body. But of course, this is a very long perspective because there are many problems that we have to face to reach this goal. And this was the project that funded this research. It was a flat open project named Plantoid. We have the University of Florence together with us. They studied the communication real plants. APFL studied the high-level control of the robot. And IBEC was a group in Spain, Barcelona, studied the chemical sensor for nitrogen and phosphate. So to conclude, clearly we are living in an era of robots. This is a special issue that The Economist published some years ago in 2014, The Rise of the Robots, describing how the future will be changed by sharing our environments with the robots. Robots that can move in domestic environment for helping elderly people, or in our factory, or in real environment to rescue, monitoring, and many other applications. But there are many problems that we have to solve. Also, moving from rigid link robots to soft material robots open, of course, a lot of new challenges. And so, as I said, we can generate new ideas, new abilities in our robot that are growth, evolution, and here again, artificial intelligence is very important to imitate the natural evolution in our robot, self-healing, but also morphing is fundamental. And this is just some example, as I say, the elongation and shortening is very useful in robotics. This is a software robot developed at Harvard University that is able to squeeze in order to move in very narrow condition, in narrow environment. It is pneumatically actuated. And resilience is a very important feature. Again, this is the Harvard group, and if they need to work in real environment, they have to be very robust, also not only soft, but they have to work in these very dangerous conditions. Jumping, this is a group again in USA, Tufts University. This is a biologist that studied the caterpillar, the movement, the locomotion, the control of the caterpillar to translate then these features in a jumping soft robot. And morphing, this is a MIT robot based on peristaltic movement that is very common in nature, also in our body, and they are very useful for locomotion in narrow environments again. Growing, this is, as I said, the first robot that is able to grow, take inspiration by roots. And the self-healing is another important feature for the robot in the future, because if they have to work for a long period of time in our environment, they have to prepare in some way. So self-healing is very important properties as well. But there are many problems, as I said, that we need to solve and address. New soft sensor, actuator, materials, modeling. This is a big issue. How we can control and model our robot. There are no rules, no books that we can open, because usually these control algorithms are for rigid robots, not for soft robots. So we have to rethink robotics. And then, of course, try to extract this morphological computational principle, and then manufacturing technology are very important to transform our prototypes in products as well, and define design rules. So how to transform, to translate biological features in design rules. This is the first challenge that we have to solve. So what is very important and evident from my point of view is that biorobotics is the evolution of the traditional robotics, even if the method is not trivial at all, because it's not just a simple copy. We need first to understand what are the principles that we want to translate in technology. If relevant, if really we improve, in some cases biology is not needed. So it's a very critical phase, this part of the initial part of the process. And what is fundamental for me, and this is a message also that I would like to share with you, of course we need different disciplines. It's important to address this complex problem just with one discipline. So we need a collaboration with other disciplines, and this is also very important for training young students. Open mind and try to understand the other people that talk in a different way. So establish a common language. This is the first point, and it's not easy. It's not easy. This is the first point that we have to establish in our group. In my group, there are different kinds of people, biologists together with engineers, experts in materials, computer scientists. But when they start, the first point is which language, in which way we can understand each other. So this is the first point, but it's needed, because otherwise we cannot go beyond. And this is my group. Some of them are, this is the Pontedera, this is the group that work on the plantoid, other work on medical robotics, biointerface. There are other activities inside the group, and of course, I thank all of them for their support and the really passion in research, and all of you for your kind attention. Thank you very much.
Thank you, Barbara. It was really fascinating lecture on challenging problem. So now, if there are comments, questions, please.
First of all, thanks a lot for the inspiring talk. I was just curious to know more about self-healing techniques of plants. I mean, how it works and whether you see that they can be adapted.
Thank you for the question. This is something that we have not started yet. The plants, the real plants, have a very fascinating strategy that can imitate in robotics also concerning self-healing. First of all, they go, the approach is the redundancy. They have many different branches or roots. When they are damaged for some reason, they simply cut. They simply remove the structure. And this is something that we could consider in the robot as well. Because if you want to develop something, again, that needs to work in a real environment, you need to implement some strategy to survive for a long time, not only energy, but also in the case of plantoid, there are several roots, and it could happen that one root doesn't work anymore. So we should, and this is also the base of the control, not only the material, in some way remove this part from the rest of the robot. So there are many strategies that we can implement, also in terms of surviving for a long period of time. As I said, they continue to grow for the entire life, so they cannot repair. In some way, they prefer to cut, to remove, because this is much more convenient. So animals need to repair, because the body is dead. We cannot change. But in many cases, except from other animals that can regenerate. But so in animals, there are many strategies to repair. And so this is something that we are also studying. This is a group in the Netherlands. The very famous are material scientists that try to apply these features in the robots. But in terms of plant inspiration, my idea is to go in redundancy as well, instead of repair.
Cut and rebuild.
Exactly.
So there is nothing similar to antibodies on human or animals?
Yes.
There is no?
No, there is not yet, even if there are some studies to imitate bacteria or microbial for developing micro robot for surgical operation inside the body. But this is more related to the surgical application.
Other question?
I believe, if I'm correct, but so for example the plants and not the animals develop a network, but they don't use it because they like the leaves, the roots develop themselves just localistically, not using information from the other roots, for example. So, like from the DNA or finding an obstacle, as you said before. So they do build a network, but then they don't use it. Am I correct?
In which sense they don't use it?
In the sense that they don't use it for sharing information with other roots.
They use it actually. They use it because they communicate with not only with other roots, and there is a very nice interaction among different kinds of species because in some ways species of plants can be enemy. And this is well known in agriculture because if you put two plants that are enemy in the same space, they try to attack each other and they don't grow. So, and they use the network to send a message in soil and exchange information with neighbors or enemy. So there is a real communication directly or using fungi. So they use the hyphen of fungi to exchange information about the condition. It seems that they use also to exchange part of the DNA. So our idea, and this is exactly the collaboration with Professor Marcapi, try to understand when they establish this collaboration, when they open and close the network with this hyphen, depending by the wellness of the plants, because this is exactly the rules that we want to implement in the algorithm. So actually they use the network. As I said, they establish the wood wide web under the soil, and this is fundamental for the quality of our environment as well. So the life under soil is fundamental for the quality of life above soil. So this network is very important actually.
Okay, so the most important is not the network within the plant, but the network where each plant is a node.
Both. We are exploring both of the condition. In particular, we started from the network inside the same root apparatus, because the question was, from an energetic point of view, what is more convenient for the plants? Moving randomly, and this is probably not, but to have a coordination in order to be more efficient in soil exploration, but avoiding energy consumption. And this is also something that we want to translate in something artificial, because this is means from an artificial point of view, having a network of robots or an algorithm that is based on energy efficiency. But the problem is the experimental part on the plants, because it's very difficult to validate these hypotheses on the real condition. So we work with the soil, and soil is very complex, as you can imagine. So we have to develop a new setup for the observation. Usually we use an agar that is transparent to observe the movement, to track the movement. So here the problem is not the artificial part, but it's the natural investigation. But yes, also the network inside the root apparatus is fundamental from an artificial point of view.
Thank you.
Thank you very much.
Are there other questions?
A very simple question, actually, curiosity. So, if I understand, you planning to have something which grows inside, say, our brain, and then with a surgery, which is very something. Are you also considering what is going to happen on these things after they're being? Are there ways of removing them, dissolve them?
Yeah. This is a nice point. We are starting to thinking, because in soil it's not needed not to come back, but in human body it could be convenient. And so the idea is, first of all, we are working the material, because of course the material is, now we use a PLA, but of course we reach 200 degrees, and so it's not possible for a human body. So we are working on material that melt, changing the viscosity at very low temperature. And the idea is to imitate something that happens in traditional colonoscopy, for example, because they extract at the end the tool. And so the idea is to come back to be really soft, and be easily extracted by pulling. So changing the characteristic of because this is really soft at the end, so that we don't need to have a very strong material inside the body. The point is to have the growth in the tip. The rest is just for creating a pipe, a tube, that is in contact with the medical doctor. But there are not really any task or so the idea is to extract the final tool, applying the traditional approach, because usually they do that. So they extract the column tool at the end of the operation. But this is just the initial idea, of course, because I know that this is the critical point, and we are working on many aspects. Of course, biocompatibility is the first point, using material that can be biocompatible, with the materials, tissue. So this is something that we are investigating. And temperature as well is a fundamental, reducing the temperature, it's a very important. So these are the main aspects that we are considering for the moment.
So there are, on the contrary, other applications where you want to keep the lighting prosthetic implant. I'm curious about that. Can you say something about that?
We have not started yet. So the medical field for us is very new, and it's nice because we start to think about the robot. The robotic route as an endoscope, because a medical doctor in Florence in the Mayer Hospital suggests us, and they say, this is an endoscope, please go in this direction, because it was not our idea. For me, it's just for soil environmental application. But yes, in principle, there are many applications which we can consider also to destroy after a while the robot. So having material that after some period can be just degraded or by our body, like in many applications, it's already in this way, or in the real field. Soil, for example, we don't need to extract the robot, we can just lose the robot and that's all. So yes, it's again the materials is fundamental in this case. We can play with the material depending by the application that we have in mind.
Other question? I have just curiosity. I mean, so you were mentioning about this starting collaboration with Piero Mancati for this model on the network. But you, for example, tell us about other cases in which, for example, when you were describing this mechanism that you discovered of growing tips, were in some way involved some mathematical models, because it just reminds me of some models that have been developing for growing shape of plants.
Exactly.
So, how much has been contributed for the developing of this from mathematical science?
I think that there are many applications, especially as you say, in controlling this growing arm, because at the end, or inspired by an octopus or a plant, what we obtained is something that is quite soft, doesn't have a rigid link, and so it's a continuum arm. And in this field, there are really, it's an open issue. There are some initial model, but very, very rude, if you want, because as I said, there is nothing applied to this kind of robotics. So we are really in a pioneering phase, and so we need to consider how the cinematic, the dynamic of this body that is able to grow. So you don't know what is really strange when we study plants is that you don't know in advance the shape of your robot. Because depending by the interaction with the environment, depending by the sensor that you implement and the tropism that you implement in the robot. So this is an advantage because you have a very high plasticity, so they continually adapt to the changing condition of the environment, but it's also a limit because you don't know the position of your end effector, you don't know, in some way you have to control your robot. So you have to really think a new way to control this kind of robot. And for the moment, we don't have a really great solution for that. So it's a very simple model, simple solution. Also because we are not really expert in math. We are more working on bioengineering and biology and material sciences. So we really need new ideas, smart ideas applied in terms of control and model of this kind of robots. And how to model also the behavior of materials. This is another way. Make a material that changes the stiffness. And depending by the environmental condition. So you have to, in some way, predict this behavior. You don't know in advance. So you have to know very well the mechanical properties of your material. So you have to characterize in a very precise way the materials, and then you have to predict the behavior of your material. So there are a lot of effort in trying to model the properties of the material, these soft materials. Because of course then you predict in some way the behavior of your robot. And so this is just to mention some of them, but there are really many aspects that we can do.
Thank you.
Thank you very much.
So if you are not, let me thank you again, Barbara. It was
Thank
very